Okay, welcome to this video, guys. Basically, this video is going to be on free vibrations for an undamped system. Okay, so if you don't know what that means, we'll get into that. Okay, so for any type of vibrating system, the most important thing that we need to figure out is what the equation of motion is. Okay, so we want to find the equation of motion for a system. Okay, and there are two methods to find it, or two main methods that we will be considering. Okay, so the first method is Newton's method. Okay, so Newton's method makes use of Newton's second law of motion. Okay, so there's a number of steps for this. Let me just jot down how we're going to go about solving the equation of motion using Newton's second law. Okay, so first we need to do is select a coordinate system, okay, for our given problem. Okay, then we need to do what we did in the last video and figure out if the masses are in static equilibrium. Okay, this is quite important. Okay, then the third step is to draw our free body diagram. Let's put a question mark to say are they in. Then we draw our free body diagram, and even we can also add under that our kinetic diagram. Okay, and then finally we apply Newton's second law. Okay, so there's two versions of Newton's second law for rectilinear motion, or for translations we can say for rectilinear systems. The form looks something like this. Sum of the forces in a given direction is equal to the mass times the acceleration in that same direction. Okay, this we are probably used to. And then for the second case, it's for rotating bodies, or let's say rotating systems rather. For rotating systems, we can say that the sum of the moments is equal to the mass moment of inertia theta double dot in a given direction, or we can have it equal to j about some point theta double dot. Okay, so some of the moments can also equal that. Okay, so that's the steps for Newton's method. We're going to go through a couple examples of these, but I just want to introduce the second method, which is the energy method. Okay, so let's call it the conservation of energy method. Okay, so an important note for the conservation of energy: it cannot have damping. Okay, so the system cannot be damped. For Newton's method, we can use it can have damping, so we can use it for any situation. But specifically for the energy method, we cannot have damping, and that's quite important. Okay, later on towards the end, we will figure out a way around this, but for now, this is how it goes. Okay, so essentially, the conservation of energy says that the total mechanical energy is conserved. Okay, therefore, the time derivative must be equal to 0. So T plus U, T is our kinetic energy, and U is our potential energy. Okay, so our kinetic and potential energy is equal to a constant. Okay, therefore, the time derivative, ddt, of T plus U must also equal 0. Okay, so that's basically it for the conservation of energy method. So the advantage of the conservation of energy method is we don't need to necessarily draw the free body diagram. We need to know what the system looks like, but we don't necessarily need the free body diagram. Okay, so with that said, I think we should get into some questions. Okay, so when I talk about the equation of motion, what do I mean? Okay, so the equation of motion for a free, undamped, unforced system looks something like this. So we have our mass, acceleration, plus kx equal to 0. Okay, so this is our equivalent mass, and this is our equivalent kinetic energy. Okay, for a rotating body, this is written as okay, so it's essentially the same thing, just we're using rotating items, not linear motion or rectilinear motion. Okay, so yeah, I think now we can just talk about some approximations or assumptions that we make. Okay, so we always use the small angle approximation. Okay, so what does a small angle approximation actually mean? Okay, so let's say we have a angle here, okay, and we say that this is angle theta. Okay, then with the small angle approximation, theta is very, very, very small. Okay, so what we can say is that this side right here, L sine theta, is actually just equal to L theta. And this is specifically for Newton's method. Okay, for different methods, we have to make slightly different approximations. Okay, for this side here, let's change colors. For this side right here, we can say that this is equal to L cos theta, which is actually equal to L. So with Newton's method, what we can say is that sine theta is equal to theta, and cos theta is equal to 1. Okay, so that's basically it for Newton's method. Let's change colors and let's talk about for conservation of energy. Okay, so for the conservation of energy systems, we can approximate sine theta once again as being equal to theta, but this time we approximate cos theta as being equal to 1 minus theta squared over 2. Okay, cool stuff. Yes, this is quite important, very important approximations, and we use them all the time, so you need to get used to this. Okay, so with that being said, I think we can get into some examples. Okay. Okay, so the examples of the first one is fairly straightforward. Okay, so we have a rod right there with a nice big point mass with a mass of m, pivots about this point. Okay, and it has a spring kt. We're going to assume this to be massless, so we have a rod which is massless and of length L. That mass is m, kt is there, and we want to get to the equation of motion. Here m is the abbreviation for the equation of motion. Okay, so that's what we have to come out with. Okay, so the easiest way to do this is, okay, so I'll do both methods. I'll do both conservation of energy and Newton's method, but first we will do conservation of energy. Okay, so let's switch colors for conservation. Let's do it in green. Okay, so we're using conservation of energy. Okay, again, the conservation of energy formula is d of dt, t plus u is equal to 0. Okay, so first of all, we need t. So t is our kinetic energy, right? So t equals half. Okay, so we are going to say that this system is a rotating system, because that would make the most sense to us. This system is rotating at an angle theta. Okay, with that in mind, we have half IA theta dot squared. Okay, and what is IA? So in this case, it's a half. Okay, so we have a point mass. The formula for point mass is m times the distance L squared. So we're going to have half times m L squared and all squared. Okay, cool. So now we've got our T. Now we just need our potential energy U. So U is going to be equal to, so potential energy. So what we need to do here now as well is just figure out what is actually happening with the spring. So is this mass in static equilibrium? Okay, so just take a moment to decide that for yourself. Okay, so how are you going to do that? Okay, so I hope everyone has an answer. Okay, so what we do is we cut this spring right here. Spring's cut. Does the mass move? So all of the weight is acting downwards. No, the mass does not move. Therefore, the mass is not in static equilibrium. So we must take it into account. Okay, so we must take that mass into account in our conservation of energy, in our potential energy. If it was in static equilibrium, we would not take it into account in the potential energy section of our energy conservation of energy method. Okay, so with that being said, we can now say that U is equal to half. We've got a spring KT theta squared plus, let's see. Okay, so with potential energy, what we're going to see is when this moves here, this point mass has moved down. Okay, so that is a loss of energy. If it moved up, we'd be gaining potential energy, but it's moving down, so there's a loss. So we actually need to say that this is minus. Okay, and it's mg, and then we need the distance. Okay, so let's say this distance right here would be L. Okay, so that's the full length times 1 minus cos theta. Okay, so this, sorry, just fix this. The distance that it's moved down is L, this full distance, minus L, which is that now, cos theta. So we're left with this part right here, which is what we need. Okay, so 1 minus cos theta gives us that distance, which is the distance that the mass has moved. So we have that. So we have L1 minus cos theta, but using our small angle approximation, cos theta equals 1 minus theta squared over 2. So this entire expression becomes a half kt theta squared minus a half mgl theta squared. Cool stuff. Now we just need to put these together and differentiate it. Okay, so what I'm going to do is I'm going to do dt, so kinetic energy. Okay, so just simple, missing a theta, fix that, ml squared theta dot squared, there we go, that looks better. Okay, so we're differentiating in terms of t, so we need to use the product rule, but we're also doing it in terms of time, not theta. So what we're left with is we bring this 2 down, so we're left with ml squared theta dot. What is the time derivative of theta dot is theta double dot. Okay, similarly with dt du dt, we're going to have differentiating this in terms of time, we're going to have kt theta, okay, and then theta dot minus mgl theta. Time derivative of theta is theta dot. Okay, now we just put these two together. So we have our equation of motion looks something like this: ml squared theta dot theta double dot plus kt theta. Okay, I'm actually going to group these together. Kt minus mgl theta theta dot is equal to 0. Okay, and then what we can do is we can cancel these theta dots because otherwise the solution is trivial. Okay, so we're left with ml squared theta double dot plus kt minus mgl theta is equal to 0. And this right here is our I equivalent. This is our kt equivalent. Okay, an important thing to do that most lecturers will like you to do is to run a units check. Okay, so what units do we expect? We're working with rotation, so we're expecting units of Newton meters. So let's carry this out. Kilograms meters squared per second squared times radians as well. Okay, so kilogram 1 of the meter second squared is equal to a newton. We're still left with a meter, and we don't really care about the radian, but okay, so we're left with essentially Newton meters. KT was in Newton meters already, so that's fine. mg is a force times a length, so Newton meters. Okay, so everything works out. And these also have the radian because of this theta. But we don't really care too much about the radians. Okay, so that was the method for potential energy, or the conservation of energy method. Okay, so now let's move over and let's run the same exercise, but this time using Newton's method. Okay, so let's run it right here next to it. So for Newton's method. Okay, so what did the question look like? Okay, so the original problem looks something like this. Massless rod, mass m, right here, and we have torsion string kt. So what can we start off by doing? So let's start off by drawing a free body diagram. And the way I'm going to draw the free body diagram, because I know that it's rotating an angle theta, I'm going to draw it relative to that rotation. So here is our free body diagram. Okay, that's supposed to be quite straight. We have mg, we have our reaction forces, but we're going to take moments about that point, so we don't care about them. Okay, this spring is going to oppose the motion. Okay, and then we can just finishing it off by putting that angle theta. Okay, so I'm going to name this point O. And now what we need to do is we need to go back and decide, is this mass in static equilibrium? And we already decided that it's not, and so we have to again take this mass into consideration in our Newton's method. So we must include. If it was not, then we would not include this. If the mass was in static equilibrium, then this mass would not be included in this free body diagram, in the sum of the moments. Okay, so let's run the moments. Sum of the moments about point O is equal to IO theta double dot. Okay, so what's our positive direction? We're taking that rotation as positive. Okay, so what moments do we have? We have a negative KT theta. Okay, we have a positive mg. And what distance is this? Because that's our moment arm, is that arm right there. That's L sine theta. So L sine theta is equal to L theta is equal to IO, which we know is m L squared theta double dot. Okay, so rearranging this, so I'm going to take all of this that way. Okay, and we're left with m L squared theta double dot plus kt minus mgl theta is equal to 0. Okay, and once again, this is our I equivalent, kt equivalent. Okay, and if we compare our solutions, boom, these same answers. Okay, good stuff. Another check that we can do, besides a unit check, is to make sure that I equivalent is greater than 0 and kt equivalent is greater than 0. If these come out as negative values, then something is wrong and you must stop and repeat. Yeah, so that's the first example that I wanted to go over. Quite a simple example, nothing too difficult compared to the next one. Okay, so the next example, okay, let's do example 2. Okay, so example 2 looks like this. I'm going to draw out the schematic first for it. So it looks something like that. We have a point mass of 2m right there. This is massless with a length L. Okay, then what we have is we've got a nice disk right here, and that's connected to a nice mass right there, a nice cart, which is connected to a spring. The spring constant of 2k. This is a mass of 2m. This is rotating about that point and has a mass of 3m and a radius of r. What am I missing? Okay, we've got another section right there, and this length here is length A. Okay, so this is the problem that we're given. Okay, so let's decide what are we gonna do. Let's do Newton's method first. So let's do Newton's method. Okay, so what do we have to do with Newton's method? Okay, first let's decide if these masses are in static equilibrium. Okay, we don't really care about this mass here or the disk, we really just care about this 2m right here. If I cut the spring, will this mass fall? Well, everything's connected, so yes, if I cut the spring, the mass is going to fall that way, it's going to move down. Okay, so this mass is in static equilibrium, and so when we do Newton's method, we can ignore, let's say, ignore the mass. We can ignore the mass when we do the sum of the moments. Okay, so the next thing that we need to do is to draw some free body diagrams. Okay, so the easiest way is to just start out by setting yourself some coordinate systems. Okay, so this question doesn't say whether the mass is rotating upwards or whether it's going downwards, but for simplicity, okay, let me annotate straight on here. I'm going to say that that rod moves downwards. Okay, so we've got an angle theta right here. I'm going to name this angle here beta, and I'm going to give this direction here the direction x. Okay, so if you're not given, you just need to make sure that this makes sense. If this moves down, the string is going to move down, so the disk is moving that direction, which is correct. If the string is moving to the left, then this mass must be moving to the left as well. Okay, so now that we've given the directions for everything, we can start drawing some free body diagrams for each thing. Okay, I'm going to start at the top mass right here, and it's going to look something like this. So we have our 2m right there. The spring is definitely going to be held pulling it backwards, so we have 2kx is our force. For this to be going in that x direction, we're going to have that t1. Okay, so that means on the disk, or for the disk, t1 must be in the opposite direction. So t1 is now in that direction for the disk. Okay, similarly, going down that way, I'm going to say that this is t2. This point here we have, I'm going to name that O dash. We have O dash in the y direction, O dash in the x direction. That's our reaction forces. Okay, T2 must be acting upwards on the rod now, and the rod is going to look something like that. It's massless. Again, our reactions, I'm going to name that point O, so we have OX going that way, and OY going that way, and we have our 2M. So we have 2mg, but I'm going to put the word ignore there. Just remind myself that we need to ignore that mass, and we don't really care what's happening with that mass. And obviously the question is to calculate the equation of motion. So we have to determine the equation of motion. Okay, so once this is done, it is time to get into some Newton's second law. Okay, I'm going to start with this. I'm going to name this 1, this system 2, and this system 3. So looking at system 1, the sum of the forces in the left direction must equal 2m in the left direction. Okay, so the forces. So we have negative 2kx plus t1 is equal to 2mx double dot. So now we need to get this in terms of t1. t1 is equal to 2mx double dot plus 2kx. Okay, cool stuff. That's all we can do there. For this disk, So for 2, I'm going to do it underneath it. Maybe I should, yeah, okay, I'll do it underneath it. We're going to say that the sum of the moments in the left direction, or what's that, counterclockwise direction, is equal to j about o dash beta double dot all in that direction. Okay, so we're saying that, remember we said that this disk is rotating like that at an angle beta, and this is rotating that way, theta. Okay, now that we know that, we've got T1 and T2. So we have T2 going in the correct direction. T2 is pulling it that way, which is what we want. So we have T2R minus T1 is the opposite direction, minus T1R is equal to J O dash beta double dot. Okay, dividing through by R, we're going to get T2 is equal to J naught dash beta double dot divided by R plus T1. Okay, and T1 I'm going to put in straight 2mx double dot plus 2kx, and that's from that equation right there. Okay, now we have T2 and just this equation of motion in terms of theta. Okay, now we've got T2. Now we need to work on system 3. So for the third system, we're going to take the sum of the moments about O equals IO theta double dot, and the system is rotating clockwise this time. Okay, so the only thing that we have is T2, and that is in the negative direction, so minus T2A, because that distance right there is A according to our diagram here. Okay, so minus T2A, and remember we're going to ignore this mass, is equal to IO. IO is going to be, we've just got that point mass at the end, so it's going to be 2m all squared theta double dot. Okay, now what I'm going to do is I'm going to substitute this into this T2n. Okay, so it might get a bit nasty, but let's go for it. So minus j naught dash beta double dot over r times a minus, remember that minus applies for everything, minus 2max double dot minus 2kx is equal to m is equal to 2mr squared theta double dot. Okay, now we need to get this all in terms of theta. So how are we going to do that? Let's get the relationship here. Okay, so the relationship here, how are we going to get this? So this, whatever distance this goes, okay, that distance there is equal to x. So the arc length formula says that x is going to be equal to r beta. Okay, and r beta is also equal to that there, which is equal to x, which is equal to a theta. Okay, so that's our relationship. So we've linked all these coordinate systems to that. So r x, so I'm just going to put that here, x equals r beta, or beta equals a theta. Okay, now we can continue. Okay, so what is J naught? So let's start with that. J naught is equal to, remember, it's half mr squared for a disk. So, but we've got half, our mass is 3mr squared. Okay, beta is going to be, beta on itself is equal to a over r theta. So we can replace beta double dot with a over r theta double dot, times that by a all over r. Okay, minus 2m a x. X is equal to a theta. So we're going to multiply that a theta double dot minus 2ka a theta, once again, equals to 2ml squared theta double dot. Okay, so let's get to simplifying these things. So we've got 2 r's at the bottom, these two cancel with this r squared. Yeah, so we have minus 3 over 2ma squared theta double dot minus 2ma squared theta double dot minus 2ka squared theta is equal to 2ml squared theta double dot. Taking all of this onto the other side of the equation, we're left with 2ml squared. I'm going to group these thetas together, plus, okay, so these two have the same ma squared, so we can add them, and they come out to be 7 over 2 ma squared. Okay, that's all theta double dot. So we've got this, we've got this, we've got this, plus 2ka squared theta is equal to 0. Okay, so that's about it. So this is our I equivalent, and this is our kt equivalent. Let us do a check here quickly. I equivalent is greater than 0, kt equivalent is greater than 0. So those two are already fine. Now let's do a units check. We've got kilograms meters squared per second squared, which as previous before is Newton meters. Here we have kilograms meters squared per second squared, Newton meters. We have K is in newtons per meter times meters squared. Cancelling out, we have Newton meters once again. So this would be our final answer. Okay, so as you can see, not so bad, or not so difficult. Okay, so that was Newton's method. Compared to the conservation of mass method, or conservation of energy rather, the method might be a bit longer, so let us try and do this with conservation of energy as well. So, conservation of energy. Okay, so I'm going to work straight off this diagram. Yeah, okay, so conservation, maybe I should, let's see if I can get this. Okay, cool stuff. Yeah, let's put it somewhere here. Okay, great stuff. Now we've got another diagram to look at. Okay, so we can work off of that diagram. Okay, so how does the conservation of energy go? So we know we have to take d dt of t plus u equals to 0. So let's figure out t. Okay, so with t, we can say that it's equal to a half. So we've got 3 different mass systems here. So we have to take each of them into consideration. Okay, so we're going to say t is equal to a half I theta dot squared. That's for this system right here. Plus a half j dash beta dot squared. That's for this disk right here. Plus a half m, or let's rather just put the 2m because of the mass, x dot squared for that system right there. Okay. Yeah, that's about it. So now let's get the relationship again. So the relationship was x is equal to r beta is equal to a theta. Okay, and then let's also just do u, because it's pretty simple. U is equal to a half, let's do the spring first, a half times 2k times x squared. Okay, and plus the mass, right? Plus this 2m. But no, so you don't include the 2m because we ignore it because it is in static equilibrium. So we ignore the mass. There's no effects due to mass because the spring has taken that into consideration. Okay, so that is our potential energy. This was our EK, this was our EP. Okay, so now what we have to do is we take dt of dt is equal to, okay, differentiate. Okay, let's first get t in terms of theta. Let's get everything in terms of theta. So t is equal to half I theta dot squared plus a half j dash beta. Beta is going to be a over r squared theta dot squared plus a half 2mx is equal to a squared theta dot squared. Okay, doing a similar thing for you, I'm going to do it right here, is a half 2k a squared theta squared. Okay, let's dt differentiating in terms of time. We're going to be left with I-O theta double dot plus J-O dash a over r squared. Okay, so the theta stays, differentiating theta dot in terms of time is theta double dot plus, take that down, we have 2ma squared theta double dot. Okay, differentiating the potential energy in terms of time, and what we're left with is, looking at this right here, we're left with 2k a squared theta dot. Okay, now we put these two together and equate it to 0. So we have I-O. So what is I-O? I-O for this point mass is 2ml squared theta double dot plus J is 3 over 2mr squared a over r squared theta double dot plus 2ma squared theta double dot plus 2ka squared theta dot equals 0. Again, we're going to start cancelling out these individual theta dots because otherwise the solution is trivial. Once those are gone, we're left with 2ml squared. Okay, these twos cancel, r squareds cancel with this r squared. Okay, so we're left with that same thing, so 7 over 2ma squared theta double dot plus, so we've done that, so we're left with 2k a squared theta is equal to 0. So we've done that. And let us compare this to Newton's method, and look, there we go. These solutions are exactly the same. Okay, so I hope this video was useful, quite a long video, but I think we got through some good examples. In the next video, we might start talking about natural frequencies and getting using the equations of motion for the system in order to determine the displacements, start adding a bit of damping maybe, do an example on that. And yeah, but I think for this video, I'm happy to leave it at that. So thanks for watching, guys.